Okay, good morning. Hello, welcome to the second week of SCAN. So this is how far, this is where we are currently at. So first leave my setup working here. Where's my pointer? There we go. So we are in our introduction to the EEG, and last week we had a brief run through the entire EEG process and then went a little bit into discuss electrical concepts and the neural origins of the EEG. And then on Friday we discussed all sorts of phenomena that you can observe in EEG using this fairly simple approach of event-related averaging, where you basically cut out at a given electrode the signal that you observe around the stimulus and then average over a lot of stimuli, a lot of trials, and look at the average. And these averages are then called event-related potentials, and we discussed that they have certain characteristics for different sensory modalities, and that in addition to these sensory evoked potentials, there exist a number of what is called cognitive event-related potentials that show some amplitude variations as a function of the context in which a given stimulus is presented. So that was kind of the basis from a more kind of theoretical side last week, and then the remainder of this EEG introduction is now devoted to more practical aspects, if you want. So we're first going to talk about aspects of data acquisition and the artifacts that you can observe in EEG data, and then what one can do about these artifacts. And once we basically discuss this data acquisition aspects, then we consider two kinds of data analytical frameworks that are often used for EEG that in a way go beyond event-related averaging at the electrode level. One where one tries to locate the electrical activity in the brain, and these analyses usually referred to as source-based analysis, and another approach that instead of doing averages or doing time averages at the electrode level, looks into frequency decomposition of the data, usually then first at the electrode level. These two can actually also be combined, but we will look at them in separate ways. Yeah, so that's essentially the remaining part for the EEG course. We might actually get through this today, maybe not quite. Let's see how it goes. And afterwards there's FMI. Good. Any questions that should be clarified from last week? We're actually down to half. Not too bad. 3 dates down to half. And I think actually today there's also in the Vorlesungsverzeichnis it says both L24, 27 where we were last week in this room, so maybe some people are in the other room. They will eventually figure it out. So questions, remarks, anything that you want to discuss before we hear more about EEG data acquisition? Yeah. I can try, although maybe you can also come closer, because I will, I'm doing this the whole day, and if I shout the whole morning, then I will be kind of exhausted by 2 p.m. So there are still places around here. I'll try hearing. You try hearing better. Good. Okay. So the outline for data acquisition and artifacts is here as follows. So we want to talk a little bit about the technical things that go into it. So EEG amplifiers, electrodes, how to deal with electrical noise. Again, a little bit about electrode impedance minimization. And then some aspects of recording and digitization and physiological artifacts. So these are all things that if you start doing your own EEG experiment, you will run into fairly early when you want to acquire data. You will meet all these things. So who's planning on doing EEG research? Okay, in which domain?
In general, like decision making.
Decision making, okay. And you?
I'm not quite sure about it, but it will be about like time perception or something.
Time perception with whom? Do you know with whom you want to do that? Or?
I don't know right.
Okay. So for those people who want to do EEG research, they will then encounter this. Everybody else, for everybody else, it's also good to know and to have a general knowledge of the field that you're working in. Good. EEG amplifiers. So need to push harder. So this is one way how EEG labs can look like. Actually, our labs here look different. This is something that I used to some pictures that I took at the Max Planck Institute when I used to work at the Max Planck Institute. What you see here is an EEG cabin, so one can do EEG recordings inside a shielded cabin. There's actually very little research whether such cabins that are thought to shield the EEG from any ambient electrical activity really help. So we actually recorded a data set when I was at the Max Planck inside and outside the cabin to compare whether there's any benefit, specifically if you use these kind of active electrodes here. And then there were some people who were motivated to analyze these data, but then motivation dropped and they did something else. So these data is still lying around. So if you feel motivated to analyze these data and compare whether one actually needs EEG cabins, let me know. You're very much invited, but please see it through and write a paper about it, and don't just say you want to do it. So that's the EEG cabin, and what you see here outside are the recording and stimulation computer. What you see inside here is the stimulation screen, which is driven by the stimulation computer, and here you see a participant sitting in front of the computer screen, and you see me applying some gel and trying to minimize the impedances. So that's how things look. We have the same system, not only of course at Max Planck, but also here at the CCNB, and it all looks very similar. I don't think we have a shielded cabin here, but I also don't think one needs shielded cabins for these active electrodes. So this is just a lot of wasted money at Max Planck, which is always the case, because Max Planck is a horrible thing in principle. So this Max Planck Society, no one needs that. It's just wasting a lot of resources, and people working there are just they didn't get what academia is about or what science is about, because science is the combination of doing research and teaching. And Max Planck Society explicitly doesn't want to do teaching, and they think they can do great science without teaching. That doesn't work. Anyway, that was a little rant about Max Planck Society, which is a horrible thing. So please stay at the universities and do something for society and not for your own well-being only. Your own well-being is also important, but also that you contribute something to society. EEG amplifiers. So you saw them on this little picture, and here you see a bigger picture. So they are basically these kind of gray kind of boxes, and they are usually driven with some battery, so that you don't need a line, so a power cord to drive them, which of course minimizes the electrical interference that you can have when you record EEG. These are actually MR compatible, so you can also put them into the MR environment, as you saw with Mario's talk on Wednesday, or in Mario's talk on Wednesday. You can record EEG together with MR, but of course the setup needs to be MR compatible, so that you don't have, there's no danger that these things are drawn to the scanner. And so they used to come in these 32 electrode amplifier settings, where you put in the leads of the electrodes. I guess by now there will be also, at one point there should be 64 electrode amplifiers, so that's not a necessity. What is important about amplifiers, which essentially take the electrical activity that is recorded in the electrode that is put onto the scalp, is that they amplify the signal and then allow it to be digitized. And the important thing is that the signals that are recorded always refer to potential differences between two sides. So it's always the question at the side of what is called the active electrode, so the electrode where you're interested in, does the potential there get more positive or negative with respect to another side? This other side is commonly referred to as the reference electrode. So the electrodes of interest are the ones that we saw then last week, always where we observe event-related potentials. And the reference electrode is the electrode that sits somewhere, and its measure and the potential differences, the potentials at the active electrodes are recorded with respect to the potential at the reference electrode. So for this electrode system that you saw there, the reference electrode is I think CZ. So it can be anywhere, as Luck puts it. No site is actually electrical neutral. So I think we will have some points about choosing reference electrode sites, but there's nothing that you can be done that you have kind of the best kind of reference electrode. In addition to a reference electrode, there's also always a ground electrode, and this ground electrode, which is also placed somewhere at the scalp, is meant to pick up any ambient electrical noise in the vicinity of the EEG recording. Because so it's picking that up. All electrodes actually pick that up, but what's happening at the ground electrode is then subtracted from everything else. So that's the logic here. So these differential amplifiers, they amplify the difference between the electrodes of interest and the ground electrode, and the difference between the reference electrode and the ground electrode. So in a kind of weird formula, what's happening is that you have these electrodes. From this, the activities at the ground electrode are subtracted. Same thing happens for the reference electrode. So both from active and reference electrodes, anything that fluctuates in terms of electrical activity in the overall setting is subtracted. And once this is taken out, the reference electrode activity is subtracted from the active electrode. So the idea is that this ambient electrical activity recorded by the ground circuit which basically acts as an antenna for electrical activity that might be due to computers in the area, or I don't know, elevators that go on or whatever. That this ambient electrical activity is picked up by ground circuit and then subtracted from both active electrode and reference electrode, and the rest, the remaining difference between active electrode and reference electrode is amplified. Yeah?
And I don't understand why the reference electrode can be elsewhere on the scope, because isn't it a different recording? If it's here or here?
Yeah, it's that's a good point. Yeah.
And how do you make it comparable?
Yeah, that's a good point. So this is really about the recording, not in terms of the analysis. So what you often do is that you record with respect to a given reference, and after acquiring the data, you re-reference the data. And there used to be different kind of ways how people do the re-referencing. So you then have basically potential time courses, and instead of leaving them as are, you subtract from all of the time courses that you have at the electrodes, you subtract some other signal that you also recorded. For example, what people used to do is record must-read electrodes, so putting electrodes here on these bones behind your ears, and subtract the activity that is recorded there, so that then everybody uses kind of the same reference electrode. However, I think much more common right now is that you instead of using this must-read electrodes, you average the activity from all electrodes together and subtract this average activity from all electrode potential time series, so that you re-reference with respect to an average electrode. Thing is, all these things, of course, influence, or the reference, of course, clearly influences what you observe on a given electrode. Hence, this is a problem for standardization of EEG recordings. But it's also discussed kind of in the literature. So there's this frontiers topic on reference electrodes by Valdez Sosa and others. It's an important point. One has to think about it if one compares one's own recording to something that one observes in the literature. But if one uses the same reference electrode after pre-processing as somebody else, then that's the same reference electrode. Other questions? Don't get all worried about the reference electrode. It's actually not that worried.
I was just wondering whether the reference electrode serves as an active electrode at the same time. I mean, it could be expert is a place where the signal originates, right? Yeah.
Yeah, so if one then re-references this, then one can look also at the reference electrode as the standard recording. Any other thing?
By saying ambient electrical activity, do we mean electrical signal without noise or something else?
No, by ambient electrical activity, I mean electrical activity that's just in the room. For example, line noise in the building or something. Anything else on reference electrodes? No. It will actually come up again. So the electrodes, these are biosemi-active electrodes. They look like this. So they have. So what is really the electrode is this, where this little hand is now, and this pin here. This is really the electrode. This is the metallic thing that in which the current and the potentials are recorded. And then the important thing is that the rest of it is essentially just a little preamplifier. So this plastic is not on, and what's in it, that's not part of the electrode proper, so it just helps the whole thing. And then the electrode leads, so the cable from the electrode basically runs in these kind of flat cables. So you here you have, I guess, 16 electrodes, and then they these cables are put next to each other in this flat cable, and this flat cable is then connected to the amplifier, and just because of this, because they are all in parallel, you then know in which location at the amplifier which electrode is connected to. So this is a different way how electrodes can look. So these are these ring electrodes. It's basically just some metallic conductive material. And that's very cute. So essentially electrodes are just conductive materials attached to some wire. And the conductive material that is used is just a metal with good conductive properties that conducts electrical activity. And something that is most commonly used are silver electrodes with a thin coating of silver chloride, and these are these AgCl electrodes. They just have very good electrical conductance or conductivity properties. So they conduct electrical activity then into the wire, and as I previously mentioned, to make sure that these electrode pins, I think we also sometimes refer to them, so these little tips here, electrode tips, I want to say not pins, tips, that they make a connection to the scalp. You put some gel in this little space between the skin of the scalp and the tip of the electrode. And this gel is also just some conductive, so electrically conductive gel, essentially. What's actually in there, I guess it's a big secret by the company, so that you don't make your own gel. So this used to be the case, and what also used to be the case is that it's essentially that you only have these non-pre-amplifying electrodes that are basically this silver chloride rings. What I think became very prominent like 10 years ago or so are active electrodes. So you've seen earlier these electrodes that have a little amplifier in them, maybe even a light for the brain products ones. And the nice thing about those is that they, because they also already amplify the signal when after it's picked up, so you don't have a lot of signal loss along the electrode leads, is that you need a lot of less gel, you have shorter preparation times, and I don't know whether you took part in a EEG experiment 15 years ago or so. There would be quite a lot of rubbing to get the hair out of the way and to get good and low impedances. With these active electrodes, it gets a lot more relaxed, and you basically just have to apply a little bit of gel and then it works. There are also systems where you don't need any gel. Some of them are saline based, so they have these electrode nets, which are popular in research with infants and kids, because there you basically just put this net into some saline solution, so some salt water essentially, and then you put it on the head and hope for the best. So in principle, the electrodes then work already with low impedances. And there are also dry electrodes now where you don't need any conductive medium to connect the scalp and the electrode. I don't have personal experience with them. I guess they are also getting better. Has anyone encountered dry electrodes in their work? No. But they exist. So I'm fairly happy with these active electrodes, because the preparation time is really quick. Yeah, but dry electrodes might be even better. Yeah, the electrodes are used to be placed according to the extended 1020 system, which I will show you in a second. What this meant is that you basically had to do some measurements on the scalp and then figure out where you have to put the electrodes. So this is what technicians, I guess, used to do until the mid-2000s. But as you've already seen on the pictures, is that we now have these electrode caps where you still have to do like 2 measurements to situate the cap in the appropriate way, but you don't have to figure out the location of each individual electrode because they are just stuck, or they are just placed within the cap, and you just have to plug the electrode in. So, and this can be improved using 3D electrode registration with respect to the participant head, which I will show you in a second. So first thing, what is this 1020 system? This is something that you will always read in papers, that people essentially place their electrodes according to the extended 1020 system. Why extended? Because usually we now record with 64 electrodes, and the 1020 system was designed for 21 electrodes. How does this system work? So the idea is that you place 21 electrodes at 10% of latitude and 20% of longitude. What these terms mean, we will see in a second. So the one baseline of this is an equator that passes through the nasion, which is this point between your eyes. The inion, which is a little protrusion in the back of your skull. So if you, in the middle of your, the backside of your head go up, you will find that there's basically where some bones of the skull meet, there's a little protrusion that's called the inion. And now we all want to touch it. And then there are the left and right periauricular points, which are points next to your ear, essentially. And then the idea is that you form an equator, basically this circle through the periauricular points and these points at the front and the back. And so these are then the equator points that define this circle. So here a little bit bigger. So here you have the nasion, here you have the periauricular point 1, periauricular point 2, and here you have the inion. So that's an equator. And then you divide the longitude line between the inion and the nasion. So this line in steps of 10%, so 10, 20, 30, 40, 50, 60, 70, 80, 90, 100%. So basically what you have to do for this is to measure this distance. I think it's usually something around 36 centimeters, is it? Then 50 would be around 18 centimeters, and this is then where electrode CZ is located. This is something that you also have to do with these electrode caps. So you basically have to find the middle between the inion and the nasion in this longitude direction, which you can measure. Here the idea is that you, of course, divide it then into steps of 10%, which for 36 centimeters would be 3.6 centimeters. And then in addition to this line, you introduce additional latitude lines that are concentric with the equator, and these are placed also at 10%. So you basically have to have the equator and then go in terms of 10% no, 20%, sorry. 20, 40, 60, 80, and done. Yeah, so that's why 20. This is confusing here with this 10. I'm not sure what that means. It should be 20. So you can see that so you can see these latitude lines here as these circuits. And where these lines meet, you then basically can place these electrodes. So this was kind of the old logic, where one obviously, as you can also, one has to think about these things a lot. And as you can tell from me trying to explain this, I never did it this way. I only ever had the electrode caps already when we acquired EEG FMI data back in Birmingham. The electrode caps were there, so we only need to place the nasion and inion, and we need to decide on the electrode cap size, which you basically determine from measuring this equator. So the way it then works in terms of the practical aspect is that you measure the equator, and then you have like 54 centimeters, 52 centimeters, 56 centimeters. These are typical equator sizes. You take the appropriate cap and you place it so that the middle electrodes are in the middle, and that CZ is at the half of the line between the nasion and the inion, and you're done. So you don't have to actually find these circle lines and all the other latitude lines, because the electrodes are just on the cap like that. But this logic of 10% in this direction, 20% in this direction is still in the name, and also what these electrode caps refer to. The electrode labels are then based on the general region where the electrodes are. So FP for frontal pole, F for frontal, C for central, P for parietal, O for occipital, T for temporal. The number essentially indexing the distance from the midline. So you can see that if you go further out from the midline, you go to higher numbers. The odd numbers are all on the left hemisphere. So this is the nose, so this is the front. So on the left you have the odd electrodes, and on the right side you have the even numbers. So remember that we looked at, for example, electrode O2, which you now know is occipital. It's on the right side and it's relatively close to the midline. The locations on the midline are labeled Z for 0. So in the middle you have the FCZ, CZ, and PZ, OZ electrodes that refer to the midline. So not that perfect. So this shows the overview again. So here you have the equator, you have the 10%, you have the periauricular points, and here you have the electrode labels. Thing is, each electrode cap, and this is what this shows, these days comes with a sheet that actually gives you the electrode labels, and has an addition to the electrode labels, has just a linear index of the electrodes, because in the end these are all just of course conductive materials which are plugged into a certain pin or a certain plug at your amplifier, and then just are mapped onto one entry in your data matrix. So these labels, they just come in because we want them to come in. In the end, it's just a linear indexed set of recording channels. These mappings between electrode names and the number of the electrode, they are always delivered with these caps, so one doesn't have to worry much about it. And actually one also should use these sheets, because just assuming that if you plug in some electrodes that this is OZ because you think so, because you've learned how the system is, yeah, why not just look into the manual? And this is kind of the manual, and it tells you exactly what the which electrode has which label according to the 1020 system. And here you can see that the reference electrode is actually FCZ, and the ground electrode here is AFZ. So that's for the ActiCap 32. As I said, we often use ActiCap 64, and there you have exactly the same kind of sheet, and then you just have more electrodes. There's also an ActiCap 128. We won't set that up, but that was a little bit annoying because it's a lot of electrodes. Now there are these electrode caps which give you a fairly good idea in terms of a standardized space where the electrodes for a given participant are. However, if you want to be even more precise and kind of want to also measure in 3D where the electrodes are, there are setups that allow you to do that. This is called, I think it's a company name, this is the Cepos system. So what you do there is that you first, based on some measurements and two sensors that you actually stick for some time onto the participant's head, you first established a plane that defines your coordinate space in 3D. Yeah? So you measure the pre-auricular or peri-auricular point right, left, and the nasion, and you use this plane to establish a zero in a 3D coordinate system, and this zero in coordinate system is then a little bit higher than this nasion and auricular point plane. And then once you have established the 0 point of your coordinate system using this magic device, which actually is kind of a stick that you hold and that interacts via sound with a sensor, then, so this is this magic stick, but you just hold the tip somewhere. It communicates via ultrasound with this reader, and by doing so, it registers where in space it is. Once you have established this coordinate system and the 0 point of this coordinate system, you can then go to each electrode and measure the distance from the 0 point of the coordinate system, so that you have readings, standardized readings for all electrodes as a distance from the 0 point of the coordinate system. And why are you doing this? Because you want to, for each participant, know exactly how far the electrode is located from a standardized 0 point. Of course, these planes through the peri-auricular points in the nasion, they are also not, I mean, the plane is the same in each participant, but of course the distance from the nasion and the auricular points might differ, but you basically cut. So you define a plane for each participant that has the same orientation, and then you measure the electrodes with respect to this plane or the ensuing 0 point. And then you have for each participant an exact location in 3D space where the EEG electrodes were situated, and you can use this information in source space analysis. So my take on this 3D localization is it's good to have. It's a little bit hard to quantify how much more information you gain from using just default electrode positions instead of using these 3D localizations, because per default, of course, if you have a standardized head, the electrodes have also their locations with respect to the 0 point. Yeah, you might find one paper somewhere in Frontiers or somewhere that looked at how much better source localization gets. But if you really want to, by using such a 3D registration, but if you really want to know how much better source localization gets, you actually would have to have a model, so meaning a physical model where you induce some electric activity somewhere and then you measure it. And I think this really has not been done, or if so, there's maybe one lab in the world that does something like that. Yeah, but you will come across it. It's also often used without a lot of things actually in cognitive neuroscience are being used and acquired always without anyone ever checking whether it actually helps. And this is one of the examples. But you feel good when you do it and you have the data, and then everybody's happy. Good. Reference electrode placement. This came up earlier. So no site is electrical neutral. The potential of a specific electrode is always relative to that reference. And what is kind of clear is that you don't want lateralized reference sites because you might have things in the brain that are not symmetric, and then if you have so for example our language activity, and then if you have a reference site on the left, then you get something very different than if you have a reference site on the right. So you usually want a central reference site. Clearly the event related potentials depend on the reference site, so we want to take account of it. And as I explained earlier, the EEG systems for recording usually have an arbitrary reference site, but then the data are usually re-reference, so the difference is taken between the recorded electrode potentials and another recorded electrode potential time series. And this difference is then what you look at. So you can also view that as earlier we had the ground electrode being taken out, and basically by this re-reference and with respect to some other electrode, you take the original effect of this recording reference electrode out of the data. So one reason to do this is, of course, that different different EEG recording setups can have different recording reference sites, and then if you record with a system like brain products that has the FCZ as the reference electrode and you compare that with a biosemi system where the reference electrode is actually further back, then by re-referencing you make the data more comparable. Yeah, and one thing that I always recommend with all these questions in terms of, this is a typical data pre-processing question, so should I do this, should I do that? I would just recommend if you, I would just in a way recommend looking at different options. So because it's a simple data processing step, and then look at whether, for example, your effects of interest, so that you have a difference in some electrodes between two conditions, whether this is there regardless of the reference site. What will, of course, change is maybe a little bit the amplitude of both conditions, but if the difference is still there, then you can feel good about choosing then one reference electrode site and just say, essentially, we also use a different re-reference site, and the effect is still there. So the effect is not due to the reference site. Of course, the amplitudes and the overall shape might change a little bit, but yeah. So that's reference electrodes. I'm taking longer than expected. Good. Let's do environmental electrical noise and then have a break. because that's, I think, quite quick. So the voltage fluctuations that are recorded on the scalp are actually quite small. So we are always talking about microvolt. So 10 to the power of -6 volt. And to basically resolve this nicely, the EEG is amplified by a factor of 10,000, which also means that ambient electrical activity, such as alternating current line noise, has some electrical activity, hence magnetic fields, and then can induce other electrical activity, is also amplified. This AC line noise of 50 Hertz in Europe and 60 Hertz in North America is, of course, very well defined. So it's at this frequency and hence can also be taken out if it is indeed present. I think these active electrodes, they in a way are also shielded nicely so that they usually don't pick up the 50 Hertz or 60 Hertz noise. In biosemi recordings, I remember seeing sometimes this 50 Hertz noise being picked up, but this I never saw that in the active electrodes with brain products. And so because you can already, when you set up the EEG without doing any analysis, you see line noise if it is present, because it has this characteristic 50 Hertz activity. Other sources of noise are, of course, CRT video monitors. These are these old video monitors from the 80s that hardly anyone uses anymore, or 90s even. LED monitors, not really clear what they do, whether they do much. I think I saw one paper that looked into the effects of LED monitors on EEG quality. And of course, you might also have other stimulation devices. For example, in somatosensory stimulation, you might have an electrical stimulus, and this electrical stimulus might also induce an artifact in the EEG recording. So you have to actually watch out for that. Solutions are usually basically turn off everything that is not required. Maybe move the recording equipment a little bit around. So sometimes you have these kind of antenna effect that, especially with the biosemi, that if you set the leads of the electrode, put the leads a little bit different, then they don't pick up this ambient electrical activity. And as I said, you might also have an electrical shielded chamber at Max Planck. They actually, so we set it up that it's electrically shielded. In the opposite department, they actually had chambers, but then put copper wire cables into the chambers, which then, of course, destroys all the shielding. So, yeah. But it's really not clear whether these electrical shielded chambers actually help anything. But they're expensive, and if you become a professor, for example, in Hamburg, you might ask them to build electrical chambers, so that electrically shielded chambers, so that they do something and you negotiate something. This is what some people do. Real story. True story. Good. Now let's have a break. If there are no current questions.
Yeah, like I have a question about the formulating of this, about the signal. Essentially, like what's the point of the ground electrode? Because you subtract it and then you add it on again, so like they would cancel out.
Yes. But so you subtract it from. So I see where you're getting it, but the thing is that you, maybe I can show that here. No, I show that here and one can see it on the screen. So, So the idea is you have one active electrode, so that's active electrode 1, and here you have something like this, plus some let's see, 50 Hertz noise. So together you have something like this. And then you have a ground electrode, which for simplicity we assume just picks up the noise. And then we have a reference electrode, so this is the ground electrode. And then we have a reference electrode, let's put that here, that does something like, let's say this. Now you subtract from both of them the activity in the ground electrode, so using some luck way of describing things, you would first subtract here the ground electrode, so to get something like this. And then subtract from the active electrode the reference electrode, so that you get, if this is like a scale of 1 and -1, you get something like this, which is a scale of 2. So that's kind of the idea.
Yeah, like I got that, but like wouldn't you get the same result if you just subtracted the original signal from the reference, because both of them pick up the ground?
Yeah.
So like it's not really.
Yeah.
Is there a point in doing it this way, or like why don't I do it directly?
Yeah, good question. Do I remember? No, I actually don't remember. This is how it's done, and there are physical reasons for doing it. We can look up again why it's like that. So that's your task. So look up why it's done in this way, and not, as you correctly say, that of course this would happen also if you do the reference electrode. But yeah, it's kind of hardwired in there like that, and there are reasons. So I just don't recall them right now. But look it up and tell us tomorrow.
I'm just wondering that maybe in case there are wires or anything on one side, and you're recording from the side where the wires are located, then the ground might not be the same. I don't know, like the ground noise.
And the one
on some electrodes stronger than on others. I don't know. Maybe to make sure that this is not the case, they subtract it separately.
So you mean essentially that the
Yeah, because we only have one electrode.
Yeah, the ground noise is fixed, but the ground knows how it's projected. So the ground noise. So it could just be that the reference electrode maybe doesn't pick up the ground noise as it's in certain other electrodes. So that there, basically, like you said, that there's some asymmetries that basically that the reference electrode. So I mean, yeah. So I mean, this could be a scenario. So assume that the reference electrodes only. So a nice example would be, so the ground noise is mapped bijectively or in a nice way to this active electrode, whereas it I mean, then one introduces some Yeah, I mean, it's hard to see the point based on how this is set up. So you figure it out. Good, but now let's have a break.